In this lesson, we will build a deep and intuitive understanding of the binomial theorem. Here is the statement. For any non-negative integer n, and any real numbers x and y, the quantity, open parenthesis, x plus y, close parenthesis, to the power n equals the sum over k equals 0 to n of the binomial coefficient n choose k times x to the n minus k times y to the k. The binomial coefficient n choose k equals n factorial over k factorial times n minus k factorial. It counts the number of ways to choose k items from n. Now, the combinatorial idea. Think of multiplying n copies of the factor, open parenthesis, x plus y, close parenthesis. When you expand, each term comes from picking either x or y from each copy. If you pick y exactly k times, and therefore x exactly n minus k times, the term looks like x to the power n minus k times y to the power k. And there are n choose k ways to choose which k positions contribute a y. The coefficients are symmetric. The value n choose k equals n choose n minus k. Choosing k items to include is the same as choosing n minus k items to leave out. The binomial coefficients live inside Pascal's triangle. Each inside entry is the sum of the two entries above it. That is, n choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k, with boundary entries equal to 1. Let us expand small powers to see the pattern. For n equals 2, we get x squared plus 2xy plus y squared. For n equals 3, x cubed plus 3x squared y plus 3xy squared plus y cubed. For n equals 4, the coefficients are 1, 4, 6, 4, 1. Two very useful properties. First, the sum of binomial coefficients equals 2 to the n. That comes from evaluating open parenthesis 1 plus 1 close parenthesis to the n. Second, the alternating sum equals 0 for n at least 1. That comes from open parenthesis 1 minus 1 close parenthesis to the n. The derivative is consistent with the binomial expansion. The derivative with respect to x of open parenthesis x plus y close parenthesis to the n equals n times open parenthesis x plus y close parenthesis to the n minus 1. If you differentiate the series term by term, you get the same expression, showing perfect agreement. Why does the binomial theorem matter? It connects multiple areas of mathematics. In combinatorics, it counts subsets and paths. In algebra, it simplifies powers of binomials. In probability, it underlies the binomial distribution. In analysis, it extends to non-integer exponents via infinite series. Key takeaway: the binomial theorem turns the power of a sum into a clean summation, with coefficients that count combinations.